I want to welcome you to the 5th year of the CalFlexHub program. We'll be talking a little about what our findings have been. Our final report will be out at the late summer. So we've been in the process of putting together research findings. I'm going to go through with you some of the goals of what we're trying to do in CalFlexHub, the stakeholder needs assessment. You'll be hearing from Sarah Outcalt. We'll be talking about the price signal development throughout the day. There's a demo in the lobby, so I'll give you an overview of what we've done there. We have done a lot of work in the field, over 200 sites. So these are apartment buildings, homes, commercial buildings. We'll be talking about our work in the field, user assessments, and grid and cost effectiveness. So I'll talk a bit in a moment about what we're actually trying to achieve in that, and then we'll talk about where this is all headed. Go ahead to the next slide. I want to start by putting the context of CalFlexHub in the context of the work we've been doing over the last 20 years and the next 5 years. We were asked to create an open signaling system after the electricity crisis in California. And Mark is here from SoCal Edison, one of our partners at the time. And we wanted to develop technology where when the prices actually increased, that customers' loads would actually reduce. So we thought that during these hot summer events, when the electric grid was really expensive, this is after we had deregulation in California, we had some problems with the market and we had brownouts. And we thought if we had price response, we could make the grid more reliable by reducing the load with prices. So that actually was conceived many decades ago. And we'll talk today about our progress in using prices to incentivize load shifting. So we started OpenADR back in the early 2000s. We developed OpenADR 1.0. We then developed 2.0 with the NIST Smart Grid Standards process. So Cal Edison, PG&E, and Honeywell were the initial founding partners of the OpenADR Alliance. And version 2.0 came out of a standards process where we gave 1.0 to a standards development organization. And in a consensus-based process, OpenADR 2.0 was developed and was used throughout California in utility programs. We also started the demand response potential study. Sarah Smith, I saw her a second ago, was involved from the very beginning. Over the last 10 years, we've been modeling shape, shift, shed, and shimmy. And we've been trying to understand how loads can help make the grid more affordable and reliable. So we're very interested in making sure that customer loads are participating, moving from hot summer demand response events to continuous load flexibility. We worked with the Department of Energy on the Grid Interactive Efficient Buildings Roadmap. So some of these things were sponsored by DOE, working nationally. And OpenADR 3 came out of the CalFlexHub program, which we'll talk about a little bit today, which was focused on prices. And we're still asking the question, is prices the right thing for all sectors? So we'll talk a little about that. And Sarah has just completed not just the 4 phases of the demand response potential, but two studies related to if California end-use customers saw prices with elastic loads, how much load shift would we get? How much load shed would we get? And so those have been sponsored by the Public Utilities Commission, and there's a webinar coming in a few weeks. So maybe your talk has a plug for that talk, because that'll be open to the public, and that is on LBL's website. And the Industrial Ag and Water Flex Hub has recently been announced, as well as we have DOE folks in the room. Raise your hand so everybody will come talk with you. So the Industrial Technologies Office has sponsored Reflex to actually invest in national capability of industrial loads to provide load flexibility and support productivity and competitiveness in industrial technologies, as well as grid integration and grid reliability and resilience. Go ahead to the next slide. We are supporting the state's goal of trying to achieve 7,000 megawatts of load shed by 2030. CalFlexHub was about this picture here of changing the time of day when we use electricity, trying to use it at a time where it's abundant and more affordable, and reduce the time when there's grid stress. We're trying to develop and demonstrate pre-commercial technologies. So we've tested over 18 different technologies, and we're supporting the use of interoperable standards to communicate the prices and partnering with industry. So our goal, good morning, is to try to help create the technology to use prices as the first line of communication with customers. Go ahead to the next slide. This is our partner. We have over 40 industrial partners and over 20 site demonstration partners. I'm not going to read them all, but many of you are in the room and many of you are online. And I want to thank everybody for being part of this. The final report, as I said, will be out in the end of the year, but this is our last symposium. But we look forward to staying in communication with all of you, working with the state and the utilities and industry to help foster the adoption of this technology. Go ahead to next. Here's our sites. We had over 95 sites, test sites, but as Jingjing Lu is going to show you, over 200 homes, so apartment buildings, homes, commercial buildings, over 900 EVs, 81 residential, 11 commercial, and 3 campuses. And this is the family of technologies. So these are HVAC systems, pool pumps, heat pumps, smart ceiling fan, predictive controls, and thermostats, batteries, chiller plants, and a wide variety of residential, multifamily, and commercial buildings. Go ahead to the next. Now I want to talk a little about OpenADR 3.0. We are, Bruce is here. Bruce is certainly the champion. Bruce and I have been talking about this, so that we're really excited that this is at this stage in maturity, because we've been talking about updating the model. It was an XML model, now it's JSON, so it's using more modern communication technology, and it's optimized for sending prices, whereas OpenADR 2A and 2B had a lot of, it was a heavy data model. So it's modernized, it's already seeing global adoption, and we've been working with the California Energy Commission with the Market-Informed Demand Automation Server called MIDAS. MIDAS was developed to enable utilities to submit their tariffs into a computer system run out of the California Energy Commission that would send prices to devices, and they came up with their own software. And so we've been working with them on OpenADR 3, which they're in the process of using for MIDAS, and in the future update of the MIDAS platform. And we've been working with them to debug the software so that we can get these prices out. These are the shapes of the prices at the bottom: a summer shape, which is low in the middle of the day and high, like our 4 to 9 time. And then a spring price might have high prices in the morning and this big dip in the middle of the day. Demand response typically helps us reduce the electric load at those high price times, but not use more at the low price times. So we really can reduce bills if we can move loads to other times of the day. So we know we need further research on understanding how different tariffs influence bills. That's one big takeaway, is we need to make bills more predictable, and customers need to minimize their risk for signing up for these programs. And it may be that we may need some sort of demand flex programs rather than tariffs for some sectors where the incentives are more clear. That is definitely one of our challenges. So we want to understand the customer experience, how to mitigate bill volatility, and how to work on demonstrating the value to the grid all at the same time through these programs. Let's go ahead to the next slide. So I'm not going to go through these slides, these pictures here, but just to let you know, we've spent a lot of time developing metrics that can demonstrate the performance of different technologies that we can compare across the portfolio. So up on the upper right is the kilowatts reduced in the home, and then in commercial, we floor area normalize it, so it's watts per square foot, and we're comparing how many kilowatts or how many watts per square foot have been reduced from these technologies where we had over 400 days of testing in the field. These tests were typically a couple of days to a couple of weeks, and some of them were many seasons across. Most of these load flex technologies use some kind of storage. So they're using the mass of the building, or a water tank like a heat pump water heater, an integrated thermal heat pump, or a big water tank at UC Merced, or they use electrical batteries. EVs are using electrical batteries for storage. Pool pumps are actually using the swimming pool itself, but they have some sort of inherent storage. We have found that most of these technologies were able to shift 20 to 80% of the load during the high price 6-hour period. The thermostat's a little bit less, and obviously how tight your home is, how good those windows are, how exposed the mass is will influence the capability of a thermostat to pre-cool and ride through. But if you're doing this every day, it's different than a DR event where you might let the temperature float up. So we need to understand what that means to do it every day. So there's we know we need longer field demonstrations. These ones are a good start. These can be cost effective, and I'll go through that in a moment. And Sarah's going to talk about these technologies can be cost effective, but we need to understand for a broader sample in the field how these perform over time. We want to make sure the user experience is understood, that the business models to deliver these, because when you use prices, it's not part of a DR program or a DF program, unless it's kind of a continuous flex program. So that's one of the challenges is what is the incentives for industry to get these things installed? So the technical maturity and the reliability, what is the persistence of savings is still a challenge. Go ahead to the next slide. So I just gave my own punchline here. These technologies can be cost effective. And in the upper right here, there's the non-communicatable, the communicating base case, or a base case that already communicates. If you already have a smart thermostat and you wanted to get dynamic pricing, we know we can do that. That's if you already have it. A lot of people don't. So they have to, what do we consider when we think about the cost effectiveness? Some heat pump water heaters, we need to add a eco port to make it communicating. Others already have that. So they're potentially cost effective. These are actually the paybacks. And again, Sarah's going to go through this with you, but I just want to prime your eyes for looking at this graph when it comes a little bit later. We need more analysis on understanding the price response capability and the hardware and software requirements to make this price responsive. We know that the business models and the persistence of savings is an issue, and we want to make sure that this is cost effective for people of different income levels. So that's another important factor. Let's go ahead to the next slide. So I want to talk a little bit about the technologies themselves. We tested things that are already on the market. Now, everything we tested was not really able to take prices before. For example, the smart thermostats we tested, they turned the price events into kind of a DR event. And they would do what they would normally do on a DR day. But our predictive controls in small commercial would look at 24 prices and control the building more intelligently. So we have a need for late stage technologies where we know we need to continue to improve the system hardening, productization, and establishment of viable commercial partnerships. But early stage technologies, more work is needed on larger scale demonstrations and evaluating the long-term performance. So predictive controls are where we look at the outside temperature, we look at the price of electricity, we look at the schedule of occupancy, and we look at the thermal mass. And these are kind of AI-based systems. Some of them use AI to move the HVAC load to times of the day when the prices are low. So the number one thing here is that we're trying to help customers reduce their bills, and we're trying to move loads to the lowest cost time of the day. That's a very simple concept. But the control system has to figure out how to do that. And that's still taking a lot of customization in commercial buildings. In residential, we can't afford that customization. So the thermostats, some of the algorithms are more intelligent than others and they have more visibility into the control algorithms. So it's something to think about. Go ahead to the next slide. We showed this graph in previous talks, and the thing I want to emphasize is that there's a variety of ways to get a price to the device. One is through like a third-party cloud or an automation service provider. The automation service provider may talk to an OEM thermostat or a heat pump water heater. And so there's a question of where's the intelligence living and who's communicating with the device. So customers want simplicity. And there's a lot of different things here. And we need to better understand the pros and cons of these different pathways for communicating with devices. We know we need to get the businesses to invest in helping to develop this technology. Customers also appreciate the load shifting when they don't notice it. So a heat pump water heater can do that if their showers are always warm. And behind the scenes, they don't really know what their heat pump water heater is doing, but they may know what their thermostat's doing. And they may look at the temperature in the house and say, well, why is it pre-cooling right now? I'm getting kind of chilly, and then I'm getting a little warm during later in the day. Or in a commercial building. So knowing how aggressively to actuate these controls is something we need to understand. Also things with thermal storage, like an integrated heat pump. When you have a big tank of water and you're using that for both space heat and water heating, that technology can provide heating and cooling without people noticing. So those kind of technologies are very good for customers, but they may have higher first costs. So we think about all of these things, about the first cost, about how hardened and how reliable are the algorithms. And we know we need a regulatory environment that has clear policy goals so the businesses know what to invest towards, and the utilities as well. Go ahead to the next slide. So this is my last slide. I want to thank everybody, and Matt Fung. I want to especially thank Matt Fung, who's our CAM. I want to thank all the partners, and I'll be doing this at the end of the day as well, but I want to welcome you and look forward to today's discussions. We want to invite you. Some of you are on our advisory committee, which will be scheduling to go through the results sometime in the next month. I mentioned the final report in August 2026. And the Industrial Ag and Water Flexibility Hub is also being launched. And Jessica Granderson is going to be talking about that little with some of you later today. So we're moving to what are the opportunities in industrial, ag, and water customers to do similar things, not necessarily price response, but what capabilities are needed for demand flexibility, and how do we demonstrate the capability of these technologies, improve them, and also understand the grid benefits. I think I didn't mention on one of my slides that we have estimated that there's about 2.7 gigawatts of load reduction, right, Sarah? Is that the number? Yeah, ish. Yeah, from the technologies tested in CalFlex, about 2.7 gigawatts. So I'm going to introduce Siva Gunda in a moment, but we have been looking at the performance of these technologies. Jingjing and Marco will talk about the power reduction, and Sarah's going to talk about the costs and the benefits, the grid impacts, as well as customer paybacks. And they could be cost effective.